To understand why quantum batteries represent such a radical departure, you first need to understand what is actually happening inside the batteries we use today. Every lithium-ion battery works through chemistry. Ions move back and forth between electrodes, creating electrical flow through chemical reactions. This process has powered our modern world, but it comes with a fundamental problem: chemical reactions degrade materials over time. Every charge and discharge cycle wears down the battery just a little bit more. That's why your phone battery gets worse after a couple of years. The chemistry itself creates the limitation. Quantum batteries abandon chemistry entirely. Instead, they store energy using the strange principles of quantum mechanics. The key effects at play are superposition and entanglement, along with controlled interactions between light and electrons. Superposition allows quantum systems to exist in multiple states simultaneously, meaning energy can be stored in ways that conventional materials simply cannot achieve. Entanglement creates connections between particles that work together in coordinated ways, and here's where things get really interesting. In a traditional battery, making it bigger typically means slower charging, because there's more material to move ions through, but quantum batteries flip this rule on its head. They actually charge faster as they grow larger, because the entangled particles cooperate more efficiently at scale. This behavior contradicts everything we know about conventional energy storage. The most significant implication, though, is what does not happen without chemical reactions, degrading materials over time. A quantum battery could theoretically maintain its performance indefinitely. No more batteries that slowly lose capacity after a few hundred cycles. The energy gets stored in quantum states rather than chemical bonds, and those quantum states do not degrade the way chemical structures do. This is not an incremental improvement. It is a complete reimagining of what a battery actually is. Here is something that sounds completely backwards at first. With the batteries we use today, making them bigger means charging takes longer. A small phone battery fills up quickly. A massive electric vehicle battery takes hours. That is just how energy storage has always worked, but quantum batteries break this rule in the most unexpected way. Daniel Tibbin, a PhD candidate at RMIT and co-author of the study, put it plainly. His team found that quantum batteries actually charge faster as they get larger. That is not how any battery works right now. It contradicts everything we expect from energy storage. The reason comes down to something researchers call superabsorption. In a conventional battery, you add energy bit by bit. It is a gradual process, but in a quantum battery, something stranger happens. The entire system can absorb light in one collective event. Think of it like the difference between filling a bucket, one cup at a time, versus having the whole bucket fill instantly from a fire hose. The quantum system does not charge piece by piece. It charges all at once as a single unit. This is what scientists mean by superextensive scaling. The charging speed does not just stay steady as the battery grows. It actually increases. The bigger the system, the faster it charges. That is the breakthrough. If this behavior holds up, as we build larger and larger quantum batteries, we could see energy storage that outperforms conventional technology by orders of magnitude. It flips the entire logic of battery design on its head. So what does an actual quantum battery look like in a lab right now? Not in some theoretical model or a computer simulation, but sitting on a workbench, drawing power from a laser beam. That question has finally been answered by a team of Australian researchers who have built something that works. The collaboration brought together scientists from CSIRO, Australia, National Science Agency, along with colleagues from RMIT University and the University of Melbourne. Dr. James Quach, a CSIRO science leader, headed up the project. He worked alongside RMIT Professor Daniel Gomez and PhD candidate Daniel Tibbin, among others, to turn abstract quantum concepts into something tangible. What they created is a small layered organic device. Think of it as a carefully engineered sandwich of materials designed to capture and hold energy using quantum mechanical principles rather than chemical reactions. The device itself is modest in size, but what it represents is enormous. This is the closest anyone has ever come to a functional quantum battery. The team published their findings in Light Science Applications on March 13, 2026. Their paper describes a working proof of concept that does three essential things: it charges, it stores energy, and it discharges that energy when needed. These might sound like basic functions, but achieving them in a quantum system is extraordinarily difficult. The fact that they pulled it off at room temperature makes the achievement even more significant. Perhaps the most striking detail is how the device charges a laser, delivers energy to it wirelessly. No cables, no physical connections, no metal contacts, just light hitting the device and transferring energy directly. This wireless charging capability points towards some remarkable possibilities. Imagine charging an electric vehicle from a distance without ever plugging anything in or powering devices in hard-to-reach locations, simply by beaming energy to them. Dr. Quach has spoken openly about his ultimate ambition. He wants to see a future where electric cars charge faster than gasoline vehicles can refuel. That kind of speed, combined with wireless delivery, would fundamentally change how we think about energy infrastructure. The prototype is still small, and it cannot hold a charge for very long. The researchers are actively working on extending that storage time, but they have proven that the core concept works. A quantum battery is no longer just a theoretical idea. It is something that exists in a laboratory right now, charging from a laser beam. How do you prove something that seems to defy conventional physics? That was the challenge facing researchers after building their quantum battery prototype. They needed to verify that superabsorption was actually happening, and they needed to do it in real time. This required some of the most sophisticated optical equipment available. The team turned to the University of Melbourne's ultrafast laser laboratory. This facility houses dual femtosecond laser amplifiers paired with tunable optical parametric amplifiers. Now that is quite a mouthful. But here is what matters: these instruments can generate pulses of light lasting just quadrillionths of a second, that is faster than a millionth of a second. The charging events they were trying to observe happen incredibly fast without this equipment. The entire process would be invisible. Professor James Hutchison and Professor Trevor Smith from the School of Chemistry led the verification effort. They used advanced spectroscopy techniques to record ultrafast signals coming from the quantum battery. Spectroscopy essentially lets scientists break down light into its component wavelengths, revealing what is happening inside a material. By analyzing these signals, they could watch the charging behavior unfold in real time. The results confirmed something remarkable. The superabsorption effect was real, and it was happening at room temperature. This was not just theoretical anymore. The lasers had captured the signature of quantum behavior in a working device. For the researchers, this verification step was essential. Anyone can make claims about what a device might do. Proving those claims requires the right tools and the right experimental approach. the ultrafast laser laboratory provided both. The race to commercialize quantum batteries is already underway, even if the technology itself is still taking shape in laboratories. Market analysts at BCC's research project that what was an $18.5 million market in 2024 will grow to over $65 million by 2030. That represents a growth rate of nearly 25% each year, which suggests that serious money is betting on this technology to succeed. What's particularly interesting is where the momentum is building. The Asia-Pacific region has emerged as the fastest-growing hub for quantum battery development, driven by substantial government and private investment in quantum research. Countries across Asia are pouring resources into next-generation energy storage, recognizing that whoever masters this technology could hold a significant advantage in everything from consumer electronics to national energy infrastructure. The field is not limited to the Australian researchers who built that first working prototype. Major technology companies have entered the arena. IBM and Google are leveraging their quantum computing expertise to explore energy storage applications. Samsung sees the potential for revolutionizing consumer electronics. Specialized quantum companies like IonQ and D-Wave Systems are contributing their own breakthroughs. The competitive landscape is becoming crowded, which typically accelerates innovation. The applications being discussed go far beyond faster charging phones. Electric vehicles represent a massive opportunity since quantum batteries could eliminate the long charging times that still deter many potential buyers. Renewable energy storage could become more practical and efficient. Medical devices that require reliable, long-lasting power sources could benefit enormously. Even aerospace applications are being explored where weight and reliability are critical factors. What all these applications share is frustration with the limitations of current lithium-ion technology, from degradation over time to safety concerns and charging constraints. So where does this technology actually stand, and when might we see it in our daily lives? The honest answer is that significant work lies ahead. Dr. James Quach has identified the most pressing challenge. Right now, his team needs to extend how long these quantum batteries can hold their stored energy. At the moment, storage time remains a critical limitation. The prototype works, it demonstrates the principle, but keeping that energy locked inside for practical durations is still a hurdle. They are actively working to overcome that challenge. Points to a broader reality. We are looking at a timeline of 10 to 15 years before quantum batteries become commercially viable. That might feel like a long wait, but it is worth remembering that transformative technologies rarely happen overnight. The path from laboratory proof of concept to consumer product involves solving problems that we cannot fully anticipate. Yet, technical complexity is one thing, scalability is another. Entirely building a tiny layered device in a controlled lab environment is worlds apart from manufacturing millions of units reliably and affordably. Manufacturing costs will need to come down dramatically. Regulatory frameworks will need to catch up with a technology that operates on principles most policymakers have never encountered: safety standards, quality control, supply chains for specialized materials. All of this infrastructure needs to be built from scratch. Yet Dr. Quach's ambition gives us a glimpse of what could be waiting on the other side. He envisions a future where electric vehicles charge faster than petrol cars can refuel at a pump. Picture that for a moment, no more waiting 40 minutes at a charging station. He also imagines devices charging wirelessly over long distances, eliminating the need for cables and plugs altogether. These are not small improvements, they represent a fundamental reimagining of how energy moves through our lives. The hurdles are real, but so is the potential. Quantum batteries could become the next great leap in clean energy. The road ahead is long, but for the first time, we can see where it might lead.